example number 27.1, and here I want to calculate the terminal voltage of the body. So it says that suppose that the body has an electromotive force of 12.0, and it has an internal resistance of 0.05 ohm, and its terminals are connected to a resistance that has the value of 3.0 ohms. So find the current in the circuit, and then also calculate the voltage, the terminal voltage of the body, right? So if you go to this equation that I already gave you, this equation here, you substitute all those values. You should calculate your current, and then if you know the current, you subtract. So again, this is the loss. So you only get this amount, that's your delta V. Now you could also calculate this delta V directly by just taking I times R. So if you take this quantity here, because we're saying that, so what this says is that this body, so think about this body as supplying E minus I times R. So that was the terminal voltage just by delta V. And the reason is because we have this internal resistance here. Okay. Now we can calculate how much amount of power gets delivered to that resistor. I think we said in the previous chapter that we calculate power by using, so remember we said power, we can calculate it by voltage times R. We can also calculate it by I squared times R. We can also calculate it as delta V squared. So you can use any of those equations. So if you use this first equation here, if you know what the current is, you multiply by the, so you get this amount of energy. So that's the power in the resistor. Then you can calculate the power that is given by, that is also lost in the internal resistor. It should be equal to that. All right. And the total power is just going to be equal to this. Now notice that if you just multiply this times I, you should also get the same value here. So this should be 12 times 3.93. It should be the same. So we say that the total power supplied by the body is equal to the power to the internal resistor plus the power that is given to the external resistor. That's just like conservation of energy. Now let's look at this next example here, 27.1. Now it says that as the body ages, notice that the internal resistance has gone from 0.05 to 2.0. How does that changes the body's ability to deliver energy? So now, do you see that the current here? So this body was supplying a current of 3.93 when the internal resistance was just 0.05. Now, notice what is happening here. At an internal resistance of 2.0, the body can only supply a current of 2.4 amps. And if you can supply a current of 2.4, then the terminal voltage has reduced a lot. So we're going from 11.8 to 7.2. And how much amount of power is going to go to the resistor has dropped from 46.3 to barely 17.3.
So why does the resistance increase over time inside the battery?
All right, so that's a good question. That's a good question. So let me share my other screen here. So let me share the screen. All right, so the question that I want to discuss here is, so why does body's internal resistance That's a very, very good question. So right now, let's draw this picture here. So again, remember that this is our circuit. And so we have a body. Now all of this is my body. And this body comes with an electromotive force and an internal resistance. This is the EMF. This is the internal. Now, notice that when I'm looking at this body here, I'm just looking at this body as a kind of a black box, right? But if you really want to look at the body, then what you should do is that you should take this body and look at it a little bit more, then you're going to see something that looks like this. And this is the plus, and this is the minus. All right. Now, when this body is connected to a resistor, what does the body do? A body simply pulls electrons from the resistor, right? So what this body is going to do is that it's going to pull electrons. So the electrons are going to be going like this. So the body simply causes the electrons to be moving around in the loop. And that's what generates the current, because remember we said that current comes from causing the electrons to move. So what the body is doing here is that, so this body has something that is called the electrochemical action. So electrochemical. So there is some chemical reaction that is taking place in here that is supplying the energy to move these electrons from here to here, right? Now, because this is happening in a cycle, so it's a process that is just going on repeatedly, right? So for example, when you charge your body, it goes to 100% charge. As you use that body, as you use your cell phone, that body is going to drop and drop and drop and drop. The key point is that so the chemical processes so as you're using your body, right, the efficiency of the chemical processes that are responsible for moving those electrons in the loop is going to get weaker and weaker and weaker over time. And so all of this is going to show up as resistance. So when we talk about an internal resistance, we're just saying that the ability of the body to move charges around is reducing, right? So for example, if the internal resistance was 0, it means that you have a perfect body, you get maximum current out of it. But as you use the body over time, the chemical processes that are responsible for generating the energy, those chemical processes get inefficient with time. And that is going to show up as some internal.
Okay, so it's not an actual resistor inside
No,
there.
no,
it's
no, no,
just
no.
Inefficiency of.
It's just, right.
Okay,
So we represent this, again, as I said, this is almost like a black box. This is just the circuit representation, right? So it doesn't really mean that there is some internal resistance, but it's just a way to model